So this is some joint work with Dan, who couldn't be here, as John mentioned, that appeared at NSTI this year. So a pretty common thing that mobile applications want to do, or providers of mobile applications want to do, is compute aggregate statistics over their entire population of users. So you can imagine having a stress tracker app installed on your phone, and the provider of this application wants to understand the relationship between its user's blood pressure and its user's Twitter habits. So essentially, each user of the stress tracker app has a private data point stored on their phone, and the provider wants to know sort of what's the relationship between these data points that are distributed over this large number of phones. The way this works today is the app running on your phone takes your private data point and sends it up to some server controlled by the stress tracker app in the cloud somewhere, and the server will compute the line of best fit sort of in the cloud. So this is good in that it gives the right answer, right? The stress tracker app provider can learn the relationship between its user's blood pressure and its user's Twitter habits, but it's bad in that the app provider learns much more than it actually needed to know. It just wanted the line of best fit, but instead it got everybody's private user data. So this talk is about how we can sort of enable the same functionality without losing everybody's privacy. So at a high level, the way the system works is we're going to have multiple aggregation servers. So imagine the App Store, the Play Store running one aggregation server and the app provider running a second aggregation server. And the way that clients interact with these servers is as follows. They sort of split their data point into pieces using a cryptographic secret sharing scheme that I'll describe. And then instead of sending your entire sort of data in the clear to one server, you split it into pieces and send one piece of your data to each of these two servers. And this allows the aggregation servers to compute the aggregate statistic of interest in such a way that they don't learn anything else. So they get the aggregate statistic, and as long as at least one of these two aggregation servers is honest, that's all that they learn. So let me sort of set up this problem a little bit more formally. The problem is as follows. We have a bunch of devices, think of millions of phones, and each phone has a private data point, xi. And we have some number of aggregation servers, so think again of the Play Store and the app provider, that want to compute some interesting function over all of the xis. Whatever system we come up with needs to satisfy a bunch of sort of security and correctness properties. So the scheme should be correct in the sense that if the servers do the right thing, they actually get the right value back, they compute the aggregate statistic that they want. It should be private in the sense that if at least one of the servers is honest, the servers only learn this aggregate statistic and nothing else. It should be robust against malicious clients in the sense that one bad client shouldn't be able to totally screw up the computation of the aggregate. So just to show what I mean here, think about a client that sends maybe a blood pressure reading that's way off the charts in an attempt to skew the aggregate statistic. We'd like to somehow protect the system against these sort of bad clients so that we can still get good numbers out even if a few of the clients do the wrong thing. So that's what I mean by robustness. And then finally, it should be efficient. And for us, efficiency really means you shouldn't need to use a lot of public key crypto or heavy tools. And on a single server, you should be able to process on the order of sort of thousands of client submissions per second. And the system Prio that we built is really the first that achieves all four of these properties at the same time. And additionally, it provides sort of support for a wide range of aggregation functions that people are interested in. So I mentioned linear regression. At the end of the talk, I'll go through a few of the other functions that we can support. So the way we do this is with sort of two new ideas. The first is a cryptographic tool called secret shared non-interactive proof. The way we use this in Prio is basically the client, when it's sending its encoded submission up to the servers, it attaches a proof that its submission is well formed, and in such a way that the proof doesn't actually leak anything about the client's private data, and it also doesn't require a lot of heavy cryptography to check. So the innovation is the observation that we don't actually need the full power of traditional cryptographic tools to solve this problem. If we sort of co-design the crypto and the protocol, we can do something much more efficient. The second idea that we leverage is that you can sort of take a system for computing private sums and use that system to compute much more interesting functions like private linear regression without too much extra work. And I'll talk about both of these things as we go. So there's a ton of related systems for private aggregation, so I thought I would mention sort of a few of the different techniques you could possibly use to solve this problem. There's a bunch of systems that use things like additively homomorphic encryption to compute private sums and other types of private statistics. There's systems that use general purpose multi-party computation, such as fair play and others. You can also use anonymous credentials or anonymous tokens in combination with an anonymizing proxy like Tor to solve this problem. And then more recently, there have been a number of pretty cool systems based on randomized response to achieve differential privacy for certain types of statistics, including one that's used in the Chromium browser. But I think as far as these 4 properties that I identified, Prio is really the first system that provides all 4 of them at the same time. Okay, so let me give you the outline of the talk. The next thing I'm going to do is present sort of a straw man solution for the problem of private sums. And then I'll explain how we add robustness to the system to protect against malicious clients. And at the end, I'll cover how you sort of extend the basic system to cover more complex statistics. So as a warm-up, again, consider the problem of just computing private sums. So every device holds a value xi, and we want to compute the sum of all the xi's without learning anything about any individual user's point xi. So as a toy example of this, think of privately measuring traffic congestion. So each user would encode their location with sort of a one-hot encoding where their value xi is 1 if they're on the Bay Bridge and it's 0 if they're not. And then the sum of all the xi's just tells you how many app users are on the Bay Bridge at that moment. So the way this works, the way you could collect this statistic in a privacy-preserving manner is as follows. We have a bunch of servers, these aggregation servers, and we're going to assume that all 3 of them don't collude, or equivalently, that at least one of the aggregation servers is honest. Again, think of the App Store is running one server and the app provider is running a second server, or you can think of maybe putting your servers in 3 different countries controlled by 3 different organizations. However you get them, you need at least one of the servers to be honest. So when the client comes online, it has its secret data value, its private data value, and I'll say the client's private data value here is 1. And what it does is it splits its value into pieces using a cryptographic secret sharing scheme. So the idea there is you pick 3 random numbers that basically sum to 1 modulo some prime. So in the real system, we use a big prime, but just to keep things simple, I'll use a small prime. And the idea behind a secret sharing scheme is that you really need all of the shares to recover the value that's being shared. So if you only see 2 of these shares, you have no idea what the client's private value is. So the first thing the client does is it splits its value into shares using a secret sharing scheme and just sends 1 of the shares to each of the servers. The servers then add this share that they receive from the client into an aggregator or an accumulator that they store locally. So the first client does that. The second client basically does the same thing. It splits its value into shares, sends 1 share to each of the servers, and the servers add these values into their accumulators. After a bunch more clients do this, the servers can just publish their accumulators at the end of the day, and all of the randomness of the secret sharing scheme will cancel out, and they'll be left with just the sum of the client's private values. So at the end of the day, the servers learn the sum of these values and they learn nothing else. So in the example, you could imagine the servers learn that there's 3 phones on the Bay Bridge, but they don't know which 3 of the phones are there. Even this relatively simple scheme gets us much of the way there. It's exactly correct in the sense that the servers actually get the right answer at the end of the day. It provides the privacy property that we wanted. The servers just learn the sum of the xi's. They don't learn anything else. And it's very efficient. The servers basically do no work. They're just doing modular additions. The problem is that it's not robust against malicious clients. So remember, we wanted to defend against clients that did the wrong thing. And in this sort of simple scheme, doesn't have that property at all. So remember, the value the client's sending is supposed to be sort of a 0-1 value. Either you're on the Bay Bridge or you're not on the Bay Bridge. But a malicious client can do whatever it wants, right? It can pick shares that add up to some large number, say, and then it can send these shares to the servers. The servers have no idea that anything has gone wrong, and as soon as they process the request from this malicious client, they'll sort of corrupt their accumulators. So basically, a single bad client using this simple scheme can undetectably corrupt the sum, and the servers won't even know which client caused the protocol to fail. Making things even worse, in real life, users often have incentives to cheat. So you can imagine using this to track ad clicks privately, or to track the popularity of certain app features privately, or collect restaurant reviews privately. There's lots of cases in which users have incentives to skew the statistic in their favor. And so typical defenses against this attack that I'll mention in a second are often pretty costly and in many cases impractical. Okay, so now let me tell you about how we provide robustness against malicious clients with this new cryptographic tool. So we've called this a secret shared non-interactive proof, or a SNIP. And the way we use SNIPs in PRIO is as follows. It's pretty similar to the strawman scheme at the beginning. So the client takes its private value, it splits it into shares, and it sends one share to each of the servers. But then before they process these shares, the servers sort of want to check that their shares actually sum to something valid. So they want to check that these numbers, if you added them up, they would sum to 0 or 1, not something big. And they want to do this without actually learning which is true. So they want to sort of check that the client's value satisfies some predicate without learning anything else about the value. So in the most general case, the servers have shares of X, using a secret sharing scheme, and they hold some predicate, I'll call it a valid predicate, that's expressed as a circuit, and they want to test if this predicate holds on X without actually learning what X is. So in the simple example that I've been using, again, the predicate just tests whether X is 0 or X is 1. So at a very high level, the way we do this is by having the client send to each of the servers a proof string. So in addition to a share of X, it sort of sends a share of a proof. Now, given these proofs and these shares of X, the servers can sort of gossip amongst themselves. And after they talk to each other a little bit, they'll either conclude that X is well-formed, in which case they'll sort of accept X, these shares of X and aggregate them. Or the servers will conclude that X is ill-formed, in which case they'll just reject the client's request and go on to processing the next one. But either way, the PRIO servers can sort of detect and reject malformed client submissions before they actually process them. And this enforces the sort of proportionality constraint that we wanted. So each client only gets to influence the aggregate statistic by as much as it should be able to. So that's at a very high level what's going on. Let me try to explain a little bit how we actually implement this. So again, just to summarize the goal of these SNIP proofs. The goal is the servers have this valid predicate and they have shares of X, and they want to check that if they added up their shares, it would sum up to something that satisfies this predicate. And they want to do this without actually learning what X is. So the sort of first tool in the cryptographer's toolbox you might go to is something called secure multi-party computation. So this is a general purpose, very powerful cryptographic tool that allows sort of 3 mutually distrusting parties to compute any function on private inputs without leaking anything else except the value of the function. So secure multi-party computation would solve this problem, but it comes at a very high cost both in terms of computation and communication between the servers. So our first observation is we don't actually need the full power of secure multi-party computation. And the reason is that we have this client that we can use to help the servers run this check. So the servers, each server only knows a share of X, but the client here knows all of X. The client knows everything because it's the one who, the client holds X in the clear. So the first idea is we can actually use the client to help the servers check the client's own work. So what the client does is it sort of imagines in its head what the servers would have seen if they did run a secure multi-party computation amongst themselves. So the client sort of simulates what the 3 servers would have said to each other if they were running a secure multi-party computation, and the client sort of writes down all the messages that the servers would have sent and received in this secure multi-party computation. After it does that, the client just sends these transcripts to each of the servers, and the servers now just have to check that the transcripts are sort of valid and consistent with each other. So we sort of reduced the problem of computing this valid circuit to the problem of just checking whether the computation was done correctly. And it turns out, so these transcripts, I should say, are the proofs that the client sends. And it turns out that checking a transcript is much, much easier than generating it. So generating the transcript in a secure multi-party computation is hard, but checking it we can do very efficiently. At a high level, the way the checking works is the servers are able to compute something like a randomized digest of the transcript. And these randomized digests have a special structural property, which is that if X is valid, these digests will all sum to 0. If X is invalid, then it's very likely that the digests will sum to something non-zero. So now we've reduced the entire checking process to just checking whether these 3 values sum to something that's equal to 0. And so the servers can just run this very lightweight check, and that checks everything else that they need to validate. So the result is the servers only have to do sort of a constant amount of communication and a constant number of rounds to check each client request. So that's how they work. Let me tell you a little bit about what the sort of efficiency gains we get over the prior techniques. So if you use sort of off-the-shelf multi-party computation the way you would need, the result would be a system where the servers have to do sort of a linear number of public key operations per client request. And this parameter m here is basically saying how complicated the valid circuit is. And this sort of general purpose multi-party computation is orders of magnitude slower than the scheme we've built. If you use sort of standard zero-knowledge proofs and commitments, this is another way to do it that I didn't describe, you get sort of, again, a lot of public key operations and a large slowdown over this scheme. You can use fancier types of zero-knowledge proofs called SNARKs that sort of remove the burden on the servers but shift a huge burden to the client, so it's sort of orders of magnitude slower for the client. And the system, this sort of SNIP technique that we use in Prio, basically removes the need for public key operations entirely at the cost of some communication between the client and the server. And it seems like for specific types of valid circuits, we may even be able to remove this communication cost too. So again, we're by co-designing the protocol and the cryptographic primitive, we can do much better than you can with general purpose, sort of more powerful cryptographic tools. So that's the theory. Let me tell you now about how this works in practice when we actually go to build it and deploy it. So we implemented this entire protocol in Go with a bunch of sort of extra optimizations that we described in the paper that's linked at the end. And we deployed this on a 5-server cluster in 5 different Amazon data centers around the world. And we set up the system to collect sort of the sum of a bunch of 0-1 values. So this is the sort of way you'd configure the system to collect telemetry data from a car or a fridge or a smart fridge or certain types of phone applications. And we implemented a bunch of variants. So we implemented a 1-server variant that has no privacy whatsoever. So this is the one where you just send your private data to the cloud. And then we implemented 3 variants that provide sort of different forms of privacy. So the first one is the strawman scheme I presented before with no robustness guarantees whatsoever. We implemented the full Prio system that provides privacy and robustness. And then we implemented the scheme that uses non-interactive zero-knowledge proofs to provide privacy and robustness using sort of the standard techniques. So the way this works, this is a graph showing basically for this 5-server cluster with servers around the world, how many submissions, client submissions, can the cluster process in a second is the size of each submission grows. So this line shows sort of standard cryptographic approaches to providing robustness sort of looks like this. The Prio system gets on the order of 50x performance improvement over the standard tools. Again, and this is because we're not using sort of public key operations at all. We can sort of remove public key crypto almost entirely from the system. A scheme with no robustness whatsoever is about 5x faster than Prio, so this shows sort of the cost of protecting against malicious clients is on the order of 5x. And then a scheme with no privacy whatsoever is about 10x faster than Prio. So this is in some sense good news, in some sense bad news. So the bad news is it's 10x slower, but the good news is it's only 10x slower. So you still sort of pay something for privacy, but you're only paying on the order of a factor of 10. And this, I think, we can even shrink a bit with some more work. In terms of the bandwidth consumption, that the amount of bits that the servers need to transmit to each other to check a proof, this is growing, sort of showing how the bandwidth consumption grows using the standard cryptographic tools. As the submission length grows, the amount servers need to communicate grows also. With Prio, the bandwidth between the servers is actually quite small. So it's, again, a constant number of bits per client request. So this is, again, why the performance is much better, is because the servers don't need to talk very much to check each client request. Okay, so the last thing I want to do is just mention how you go from sort of private sums, which I described already, to more interesting and more complicated aggregate statistics. So using many known techniques, it's true that if you can compute private sums, you can compute things like averages and variance, standard deviation. You can compute the most popular value or heavy hitters or the min and max approximately. You can compute the R-squared coefficient of a model. You can compute least squares regression, and you can even do certain types of stochastic gradient descent. So you can do a whole bunch of things just from a system that computes private sums. So since it's not immediately obvious that this is true, I thought I would just give one example of an encoding that shows how you can compute an interesting statistic from private sums. So this is how you compute average and variance just given a system for computing sums. So here, again, each client holds a value xi, and say we want to compute the average and the variance of these xi's. The way we do this is by having each client encode her value x is this pair x and x squared. And checking this encoding is actually very straightforward. You just have to check that basically x squared minus y, so the first component squared minus the second component is equal to 0. That checks that the encoding is valid. And then you can use Prio to compute the sum of these encodings. So you sum up all the xi's and you sum up all the yi's. And if you look at what you get at the end, you see that basically the sum of all the xi's, if you norm out by the number of clients, just gives you the average. From the sum of all the yi's, again, norming by n, gives you the average of the x's squared. And then you can compute the variance in the standard way. Given the sum of the x's and the x's squared, the variance just falls out. So this is just one example. In the paper, we show sort of a bunch of other statistics that have sort of simple valid predicates that are easy to check, but still let you do interesting things. I should mention that Prio, this type of system, can't compute all statistics efficiently. So there's things like exact median or exact min and exact max that we actually have arguments in the paper to show why this sort of system will not be able to compute that type of statistic, but I'll point you to the paper. Again, the link will be at the end for the details on that. So just to summarize sort of what happened, we're in a world today where you just send all of your private data to some cloud server for the purposes of them computing an aggregate statistic. And with this new type of system for private aggregation, the idea is that you sort of share your trust amongst multiple aggregators. So you send a piece of your data here and a piece of your data there. And as long as one of the servers you talk to is honest, all that the servers will learn is this aggregate statistic. So you can sort of give the servers the functionality that they want. Your app provider can compute the aggregate statistic it wants, but it doesn't need to learn all of your extra private data that it didn't actually need anyways. So I think wholesale collection of sensitive user data, as is happening now with our sensors and our phones, really puts our security at risk. And the system called Prio is sort of a step in the direction of removing this risk. So we provide these 4 properties I mentioned using 2 new cryptographic techniques, this new proof technique and some new encodings. And I think together these techniques bring private aggregation much closer than it has ever been to practical. So thanks, and happy to take your questions now.
I'll do it.
Microphones coming in and hands going up. So let's go.
So you mentioned how you build in, I'm coming from here.
Yeah.
So you mentioned how you achieve robustness by having the client do the secure multi-party computation. So if the client is malicious, is it not possible for them to subvert that process?
Yeah, good question. So it takes an argument. So basically what we have to show is that even if the client does the simulation incorrectly and sends the wrong values to the servers, it'll get caught with very high probability. So even if the client cheats in constructing these transcripts, even then the client will get caught almost always. And you can sort of choose what failure probability you want, and you can drive it as low as you need.
Related to that, can you talk about how you tune that probability? What the cost is to tuning it?
Yeah, so the failure probability is sort of exponentially small in the amount of work that the servers need to do. So if the servers if you double the amount of traffic between the servers, you sort of cut the failure probability by an exponential amount.
Question in front here.
Practically speaking, could you show me the limit of the number of servers? It's in some sense a very silly question, but
Like how, the limit in the number of servers in which way? Like, I mean, I guess, so the system can support any number of servers you want, and the cost of everything basically scales linearly in the number of servers you have. I think in practice, you're probably not going to use too many servers just because the sort of availability of the system depends on all the servers being around. So there's sort of a trade-off between how weak you want your privacy guarantees, or how strong you want your privacy guarantees to be, and how tolerant you want the system to be to server failure. So there's sort of a trade-off there that you have to take into account.
Thanks.
All right.
What's in the client-generated transcripts that allow the servers to verify that the content is valid?
So how specifically do you construct the transcripts?
Yeah.
It's basically just, if you look at sort of the multi-party computation protocols, there's one specific protocol that we use, but it's almost exactly the messages that the servers would have sent to each other in the multi-party computation protocol. So there's, say if there's 3 servers, the transcript that server A receives is every message that server A would have sent and received in this execution of the protocol. We can actually compress it a bit, but that's pretty much what it is. So the servers get exactly the transcript that they would have seen had they been participating in this protocol.
Maybe one more question here. I guess next question period. If you have a question and you raise your hand, we can get you a microphone before it's your turn to answer.
Hi, you mentioned for the server, at least one server need to be honest. So why that's the case? If, like, for example, if one server like send ridiculous large amount of value, won't the whole sum become garbage?
Right. So the robustness property is to protect against malicious clients. So we don't protect against we don't protect robustness against malicious servers. So the privacy property holds as long as one server is honest, but any of the servers can sort of give you the wrong answer. So you could modify the scheme to also protect robustness against malicious servers, but in practice, it seemed like that wasn't really worth the cost because, you know, if your server is bad, it can cause problems in many more creative ways than that. So we sort of thought that whereas the clients, there's millions of clients, and protecting against bad clients is somehow much more important for practice. But it's a good question.
Great. Okay, thanks. Why don't we thank
Yeah.
Corrigan?